Every day we face hurdles in our life and problems that require new approaches or breakthrough innovations. In this podcast series, we're going to meet people that take audacious swings for the fence because they believe that changing the game is their personal responsibility. They believe it is up to them to be the solution. Hi, I'm Mark Forche. I'm the president and CEO of Delphinus, and welcome to our Be the Solution podcast. We're at the Delphinus headquarters today, quiet Saturday morning, and I'm joined by the two co-founders of Delphinus, Drs. Neb Durek and Peter Littrup. Neb and Peter, if you would, maybe for the viewers, just describe your background.
Sure. I'm a professor of radiology and oncology at Wayne State University and director of tumor ablation at Ascension Providence Rochester Hospital.
Awesome.
And I am a professor and vice chair for research in the Department of Imaging Sciences at the University of Rochester. Started out life as an astrophysicist before embarking on this endeavor with Peter. And now mainly focused on seeing how we can get SoftVue going.
Yeah. So in a way, this is rocket science a little bit. So listen, you two both took a pretty audacious swing for the fence with the founding of this company and the creation of this technology, and started as a vision on a piece of paper as a hand sketch. But you were both at Wayne State Cromanos and didn't really even know each other. So how did you meet, and where did the vision for SoftVue come from?
Well, Peter and I first met at a workshop that was actually sponsored by the Cromanos Cancer Institute while I was still doing astrophysics at the University of New Mexico. And that's where I met Peter. And it was interesting because, Peter's an MD and I'm a PhD. And so Peter actually coined the term spaceman meets the Iceman, because at the time he was also freezing tumors as well, doing cryo. And so Iceman and Spaceman got together, and things evolved from there. So.
Yeah, this was a pretty cool brainstorming conference that we had for a couple of years in a row, basically trying to get together a lot of the best minds of the national labs and to see where could you make the biggest difference with technology and medicine.
Yeah. So you took on the challenge of a category, ultrasound, that has been around for a long time, has a lot of applications, and some people might look at it and say that doesn't seem broken. What was your inspiration, maybe as a target for this use, and what was the problem that you sought to solve?
Well, from my perspective, I had already done a lot of work with prostate ultrasound and screening and detection. And here was a room full of brilliant people saying, well, we really haven't assessed what we can do with ultrasound with where we stand, which then brought into, well, what if we threw at it enough computer horsepower?
Yeah, so from a physics perspective, I think the challenge to me was one of recognizing from a physics perspective that there's things ultrasound isn't doing right. For one thing, it's not correcting for aberrations. These are things that make the ultrasound image blurry. And during my astrophysics days, I worked a lot on how to de-blur images. Stars twinkle, and that's not a good thing if you're trying to image something, because it's a blurring process. And astronomers have developed techniques for de-blurring images. And the idea was to try some of those techniques on ultrasound and improve the situation that way.
So why specifically the focus on dense breast as a challenge, and the screening capability of dense breast? What was maybe not satisfactory in that space for you to take on a big technological challenge?
Well, the problem with dense breast is that it makes it more difficult to find cancers, and thereby, when you look at it, it's also the more common. So the more dense your breasts, the more likely you are to have cancer, the more likely you are to miss it. And so if we could then be able to see through the breast with adequate ultrasound, well, that's a whole new concept of ultrasound. Rather than just bouncing signals off and reading them back, we're actually seeing through the breast and can get quantitative measures like sound speed and attenuation.
So is what you just said, was that kind of the hypothesis that if you could see through the breast, you can understand character better? And if so, then you created some very novel technological approaches. So tell me about that. What was the technology solution that you envisioned to try and deliver something different?
Well, I think the best answer for that can be phrased as a challenge, because we were told initially by one fairly famous scientist, which will go nameless, that you'll never get a sound through the breast. No way. It's just impossible, especially a dense breast. It's just not going to happen. And so, and our solution to that was just to use low frequency waves, because low frequencies can go through the breast unimpeded, relatively speaking. And then the answer came back again from the person who should be unnamed, that, well, there's no way that low frequencies you're ever going to get decent resolution, right? So here we are today using low frequencies with sub-millimeter resolution. We took that as a challenge. That was the gauntlet that was laid down, and we took it on.
Yeah. Yeah.
And the only way that you can actually see all the way around the breast is with a ring array. And so that ring array allows some of these sophisticated algorithms to be able to see sub-millimeter. As a practicing radiologist who loved ultrasound, I fully understood that why they were in this realm of, well, you got to see things at ultra high frequency in order to see what it is you want to see, but they didn't understand that with some of the tricks of transmission imaging, you could actually get more information out of that.
So ring array as a solution, but I mean, before you prove it, it's kind of a hypothesis that that's going to actually deliver what you want it to deliver. So you created it. I mean, I've seen the prototype, and it's a fairly let's call it not pretty, a prototype. But then there's a point in time at which you're working on that. What massive hurdles in executing that vision did you have? What kind of things did you, ring array, data management, what kind of things did you have to leap over as walls?
Well, the biggest technical challenge was how do you get to these sub-millimeter images, given the fact you have a ring array, given the fact that you have this fairly crude prototype. And I think the best way to answer that question is that what we're really trying to do is solve what mathematicians call an inverse problem. That is, you surround an object with sensors, in our case a ring array, and then you take measurements along the surface, and then you try to infer what the interior properties, what it is you're looking at, what are the properties of the tissue inside. And in our case, we solved the acoustic wave equation. And the trick to that is that in order to get a good image, you need lots and lots of sensors. So that's why a ring array has 2,048 sensors on it. And you need to be able to transmit and receive on all of those. But what you get out of that is a really huge data set. And how do you take that data set and create an image in a reasonable amount of time, right? And that's what the challenge was. And that's where it was really important that we develop technical solutions as well as mathematical solutions to help it. Because as the old NASA adage goes, faster, cheaper, better, pick two, right?
Yeah.
And so we picked two, and we optimized it, and we got the sub-millimeter images. But with Moore's law and things getting more and more efficient all the time, we're actually going to get all three of those over time: faster, cheaper, and better.
Yeah. So Moore's law. You went through iterations of this in the lab and in the work that you did, and then ultimately it became a system that went into a clinical trial. And so you're standing in front of something which is kind of your proof of what the hypothesis, how you achieved against the hypothesis. What did you hope for in the clinical trial as the outcome? And what did you get as, did it prove out for you what you envisioned?
I mean, when I look back at it, it was a big step to try to run a screening trial because you'd barely quantified the images. We were very happy with the prototype despite the way that it looked at the time, because it proved that you could function in a busy radiology practice. And having been a practicing breast radiologist, you don't have much time during the day to actually stop and double check things. This thing has to be run almost independently. So we were already up to speed. We knew we could do the trial, but then what would the outcomes be? Because everything with ultrasound up until that point had produced too many false positives. Standard ultrasound was good at finding additional cancers, but then could it actually avoid the problems that they had of too many false positives resulting in too many biopsies? And that was, I think, the real hurdle we came over, was finding 20% additional cancers with 8% better specificity, or the real potential to reduce unnecessary biopsies.
Because when we first started this, we were hoping, maybe, for us, the ultimate milestone would be, can we save a life with this? We weren't even thinking necessarily about screening. Initially we thought it was a diagnostic tool, and then build from there to screening. So that to see it come to fruition in this huge 10,000 patient trial and prove itself out, that was the ultimate thing for us.
Yeah. So you went into this hoping that you could improve sensitivity and specificity, and got that outcome, which was satisfactory to proving out your hypothesis.
Actually, sorry to interrupt, but I think what the actual expectation was that we would lose in specificity, but not as much as regular ultrasound. We didn't think we'd actually gain the specificity. That was a very positive outcome.
So the other thing is you create a technology that has all these novel characteristics. I mean, there's really, it looks unlike anything else. So, were there other things that you discovered, like as you were working through this and looking at images and seeing the different data sets? Were there unexpected findings, things that you didn't anticipate necessarily to see?
I can start if you want.
Well, I was always fascinated by the concept of, because we were looking at things with basically a triad of standard reflection. Okay, we should be as good as standard reflection ultrasound, because now we're seeing the whole breast. But we're adding two new components that are quantitative: sound speed and attenuation. But attenuation is a little bit tricky, and we actually turned that into what we call stiffness fusion. And being able to get full breast stiffness, something that's never been done before. So now that brings us into a whole new category, and that's what we're exploring right now. And we've already published on some of the stiffness aspects of whole breast imaging, as well as finding out that about 95% of cancers arise at this fat glandular interface. And so that is, we know where to look. Now we've got whole new quantitative parameters on how to assess the ultrasound images.
And do you believe that's a result of having more information, different information, kind of a different way of seeing things that you've...
Yeah, I mean, when you look at it with the triad, we didn't expect that the 2/3 that we didn't understand of sound speed and attenuation actually contributed so much to finding the cancers and then characterizing the masses that we found to know whether they're worthy of biopsy.
And the finding that cancers form at this interface, they're not randomly located within the breast, but in specific regions of the breast. That was really unexpected, because you don't see that in mammography. Because mammography, all the tissue folds over because of the compression, and it masks the fact that these cancers are at this particular location. So that was a big thing, and I think it's going to really help speed up workflow associated with reading our images in a screening setting, because there's a preferential area of where radiologists can now look.
Yeah. So you mentioned workflow, and thinking about, now there's a new modality. It's something very different. Thinking about workflow and introducing this into clinical practice. So this is a new and different approach. What kind of things do you look at and see as challenges there, and in what way does this address that?
Well, when I look at it as far as, how you run a breast center, the fact that our indication has it that we can actually obtain the ultrasound at the time that you're getting the mammography makes it much smoother to go through than what the GE and Venia previous PMA approval for screening basically showed. And that was limited to you have to get the mammography first. Now you can do it all in one sitting, and it really doesn't interrupt the radiologist, and you don't have to have a sonographer to run the machine. So this is actually a practice of screening that is, basically on autopilot.
And again, this is where Moore's Law is going to help us a lot as we move forward, because right now, we can get roughly 2 patients per hour, 60 per week. But in the future, we can do better, because as our ability to do more computations per dollar or per unit time, it means that we'll be able to produce images faster. So we'll be able then to get 4 patients per hour, or maybe even more.
So you've mentioned Moore's Law a couple of times, and I also think of in any startup the different walls that you face and the different barriers that you face and challenges, and it's not easy. Not everybody's cut out to be an entrepreneur or innovator or kind of jump over the big walls. When faced with a lot of these challenges at one point, why didn't you give up? Why did you keep swinging?
Well, from a simplistic point of view, since I'm not as bright as the people who are actually doing the equations, I looked at Moore's Law as the surfboard, and we were surfing the great waves of science. And can it be done? Yes, we got that done. Should it be done? Well, that's why we were in it in the first place. Absolutely. Find cancers, save lives. And yet at the same time, that run out of the wave, we're at that run out now. It's like we bet on Moore's Law to begin with. Yeah, there was computational things we didn't understand, but the fact that we're there now, it's like having a great ride on a wave, and the timing is perfect.
It was really like a roller coaster ride. There were ups and downs, and every time there was a down, which is I think what you're referring to, I think there were multiple times at which the whole thing could have stopped, right? And I think what kept me going in particular, kept us going in general, is we looked at how much we already accomplished and where we started from, and it was this huge increment in technology. And so what's to say that we can't do another increment later, right? Especially with Moore's Law on our side. And so that gave us encouragement. The fact that we got this far already, we can certainly go for more. And the other is simply the fact that people naysayed things, right? People who told us we couldn't do it. That's just a gauntlet you throw down. That's really just a challenge you accept, right? You don't go down without a fight.
Yeah.
And so that was really, there was a combination of those things.
Yeah, absolutely. So maybe another question. Innovators innovate, right? So nobody's ever completely happy with the canvas they've painted on and the painting that they just delivered. So you think about this foundation of things. What's next? What do you see in the future here? Are there places to go?
Well, before we go to that, I'm still enthused of that. We got such a long way to go to improve our images and have a big running room. Standard ultrasound, as an example, has been iterating for so many years. They don't got too much more to go, but with Moore's Law and being able to continually improve the processing and the analysis of these images, we've only just begun. So to move that forward, image quality is going to continue to get better, which is going to continue to produce radiology detected masses and cancers and finding them in women with dense breasts. And that is a given right now. We're good to go for screening, which I think was something we almost didn't dream of, that we could actually get to that point. But now that we've gotten there, we can let further things loose, whether that be artificial intelligence, AI, being able to help analyze these images faster. So it's not just scanning faster, but scanning better.
Well, it's truly a platform technology, as you mentioned. And I think the fact that it's computationally bounded means, as Peter said, we continue to surf and get things better. But it's that the ability to improve over time without a huge amount of effort is what the beauty of this platform technology is, because you can't do that with X-ray technology because you're dose limited. You cannot increase the dose to make the image better. You can't do it with MRI, not very easily, because you have to keep increasing the strength of the magnet, and it gets really exponentially expensive when you do that. It just isn't practical. And so from that aspect, it's something that's shared, that we have, that no other competing technology has. Not even regular ultrasound, because regular ultrasound is not computationally bounded. It's technologically bounded. And so, and then because it's a platform technology, we can look at other uses. We can look at the entire breast cancer management continuum and say, okay, can we measure breast density, which is in turn a measure of breast cancer risk? We can measure women's lifetime more accurately, a lifetime chance of getting breast cancer in the first place. We can monitor therapy, for example, using this technology. And then looking further down the road, we can also try to apply this technology to other organs. There's an unmet need in prostate cancer screening, for example. Maybe you can use something similar, adapt this to that. There's brain imaging, for example, would be a natural next step as well. And so there's potential to address other diseases, other parts of the body, maybe even the whole body someday, right? And so that's why it's such an open-ended thing, because it is a platform technology.
Well, look, I mean, number one, I applaud both of you for taking the audacious swing for the fence, looking at a category where things are exactly seem maybe okay, but room to improve. But you took a really audacious path to create an innovation and be the solution to the challenges that that radiologists face, patients face, and that technology faced. And I mean, that's an incredible thing. So I'd like to thank all of you for joining us for this, and hope this has helped inspired you to think a little bit about challenges, technology that needs to be created. And I think one of the things about this series is that as we look at challenges that exist, we can't really depend on other people to do it for us. We really need to take those on. And so we're talking with innovators and entrepreneurs that are the solutions for those challenges. So thanks for joining us.